Midnight had arrived on October 1st, 2025, and with it came a silence that no one watching the clocks could have anticipated. NASA, the agency whose voice carried the authority of the stars themselves, had gone offline. Every website, every press feed, every automated ticker that normally flowed with the rhythm of space news fell abruptly silent. The official homepage bore a stark declaration: government shutdown. But in the void left by human administration, the cosmos proceeded, as always, indifferent to the artificial constructs of law and bureaucracy. At that same hour, a visitor from far beyond the solar system pierced the veil of our neighborhood, a body not born of our sun, but traveling across light years to slip past Mars's orbit with uncanny precision. The timing, almost theatrically cruel, left the public gaze suspended between wonder and unease. What appeared at first glance to be mere coincidence, the cold enforcement of a fiscal code, felt suddenly intimate, cosmic, and unsettling. Outside observers, European orbiters, and a skeleton crew at NASA tracked the interstellar traveler silently, instruments recording photons and trajectories in a world suddenly muted. The rare visitor, designated 3I Atlas, had entered its once-in-a-lifetime corridor for observation, sweeping within 30 million kilometers of Mars, a distance close enough to allow meticulous measurement, yet far enough to remain untouchable by hardware. In this ephemeral window, the red planet transformed from a quiet outpost into the most attentive observatory of the inner solar system. Scientists, technicians, and citizen astronomers alike were rendered invisible actors in a drama of precision, suspense, and profound existential curiosity, observing an object that would neither wait nor slow for humanity's schedules or procedural pauses. For 7 days, Mars became a stage, 3I Atlas, the solitary performer, and the world outside was left to wonder what secrets the universe might whisper in the absence of its usual narrators. The arrival of 3I Atlas marked only the third confirmed interstellar object ever detected within the human observational record, a rarity that makes every moment of its passage almost unbearably precious. Unlike ordinary comets and asteroids, which orbit the Sun predictably and have lifespans measured in generations of observation, interstellar visitors are anomalies, statistical outliers in the vast continuum of solar system dynamics. Each carries with it the weight of a story written across light years, a chemical and physical biography forged in environments far colder, far more violent, and entirely alien to our Sun's familiar warmth. The trajectory of 3I Atlas revealed a hyperbolic path, inbound from a region of space beyond the influence of our planetary neighborhood. Early measurements indicated velocities impossible to reconcile with the standard gravitational architecture of the solar system. Its motion was deliberate, unbound, and indifferent to the planets it passed. Mars merely offered a fleeting vantage point, a chance to capture subtle light curves and spectral signatures that might hint at its origins. Observers across Chile, Europe, and Asia calibrated telescopes to follow every movement, noting its brightness, color, and coma evolution with precision unmatched for any terrestrial body. In the sterile light of a computer screen or the quiet hum of an observatory, scientists could only marvel at the alien choreography, each calculation a careful negotiation with physics itself. The object's rarity magnified the stakes. Any missed observation could erase years of planning and leave questions that would linger for decades. And yet, its silent passage was simultaneously terrifying and exhilarating, a reminder that, while humanity can catalogue, calculate, and theorize, the universe remains vast, indifferent, and full of mysteries that arrive unannounced, bound by nothing but their own laws and momentum. The universe, vast and ancient, is governed by patterns so regular that astronomers often speak of them as comforting constants orbital resonances, predictable cometary returns, and the steady rhythm of planetary motion. Yet every so often, a statistical outlier appears, a visitor whose path refuses to conform, whose existence challenges the assumption that we understand the mechanics of our cosmic neighborhood. 3I Atlas was one such anomaly. Amid billions of comets and asteroids, each sculpted and constrained by the sun's gravity, only a minuscule handful trace trajectories that no planet, belt, or known dynamical force could account for. The odds against encountering an interstellar object are staggering, yet here it was, tracing a hyperbolic arc through space, its origin and composition hinting at a violent birthplace far beyond the solar system. Scientists were both fascinated and unsettled. The rarity magnified the implications. Every observation carried disproportionate weight, every gap in data a potential missed revelation. For centuries, humanity had catalogued comets as predictable wanderers, their eccentricities small, their compositions familiar. In contrast, 3I Atlas represented the unknown, a visitor whose motion suggested neither family nor familiarity, only the alien logic of interstellar physics. Its presence demanded an acute awareness of uncertainty, the recognition that our models, no matter how precise, could only approximate a universe that occasionally produced phenomena entirely outside expectation. In this context, Mars was transformed from a distant, static observer into a crucial witness to an event that could refine, challenge, or even upend fundamental assumptions about the frequency, nature, and chemistry of objects born beyond our Sun's influence. Mars, usually a silent witness to humanity's robotic emissaries, became for one fleeting week the preeminent observatory of the solar system. Its orbiters and landers, instruments designed for atmospheric studies, geological surveys, and climate monitoring, were repurposed to follow a visitor that would not wait for convenience or protocol. In this brief window, the geometry aligned perfectly. The path of 3I Atlas swept within 30 million kilometers, close enough for subtle measurements, yet safely beyond any risk of collision. The planet itself, red and familiar, transformed into a lens through which the cosmos revealed a fragment of its wider, interstellar narrative. Every orbit of Mars now carried significance. Every rotation of its satellites and every adjustment of their pointing sequences became a calculation of extreme precision. Engineers and scientists coordinated across continents, issuing commands, checking telemetry, and verifying instrument health in a choreography timed to the rhythms of the visitor. The stakes were existential in scale, not for human survival, but for knowledge, for the rare opportunity to observe matter formed in a realm completely outside our Sun's dominion. For a moment, the dust storms, icy polar caps, and thin atmosphere of Mars receded into secondary importance. The planet's orbital mechanics, its trajectory around the Sun, and its precise rotational period became essential variables in a cosmic experiment that had no repeat. As photons from 3I Atlas passed within the planet's observational corridor, every detector became a witness to the unknown, translating the faint glimmer of distant ice and dust into data that might illuminate the physics, chemistry, and history of a world that had traveled across interstellar space to greet a neighbor it would soon leave behind. Mars was both stage and participant in a rare alignment, a fleeting intermediary between the known and the unknowable. The first hints of 3I Atlas appeared quietly in the nightly logs of the Atlas survey in Chile on July 1, 2025. A faint point of light, unremarkable to the casual observer, exhibited motion that refused to fit any known orbital model. Its early positions, measured over a handful of nights, produced curves that stretched farther from the Sun than any typical comet or asteroid. suggesting a trajectory unbound by the familiar gravitational web of the solar system. As astronomers tracked its progress, the object revealed subtle anomalies, shifts in brightness that hinted at rotation, minor variations in color that suggested complex composition, and a hyperbolic orbit that unequivocally marked it as an interstellar visitor. Over the next 3 months, observatories across the globe contributed data right ascension, declination, photometric points feeding into orbital calculations that would eventually confirm its inbound path. Every measurement carried weight, every observation was scrutinized for error, and every prediction was tested against new readings. The object's hyperbolic trajectory distinguished it not merely as a rare comet, but as a messenger from a realm entirely foreign to our solar system, a fragment of another stellar system passing through, transient and immutable. Its arrival initiated a cascade of preparation. Mars, orbiting satellites, adjusted schedules, European and American science teams coordinated observation campaigns, and citizen astronomers were drawn into a collective vigilance. From these earliest detections, 3I Atlas's passage was framed not as a routine astronomical event, but as a fleeting opportunity to study matter formed under conditions vastly different from our own, a chance to probe the architecture of distant space in a week-long window that would vanish as quickly as it had arrived. As July transitioned into the summer months of the Southern Hemisphere, the global astronomical community rallied to refine the trajectory of 3I Atlas. Observatories from Chile to Spain, from Hawaii to Japan, contributed meticulously timed measurements, each data point a piece of a fragile mosaic. Right ascension and declination readings were fed into dynamic models, photometric brightness values catalogued, and light curves analyzed for rotational signatures. Each observatory brought unique capabilities. Some offered high-resolution imaging, capturing subtle coma asymmetries. Others provided spectrographic data, hinting at molecular composition and thermal characteristics. Despite the collective effort, early calculations revealed the persistent uncertainty inherent in observing a body traveling on a hyperbolic trajectory. Even minor observational errors could translate into vast differences in predicted position, magnifying the tension for the impending Mars window. Astronomers communicated continuously, sharing updated ephemerides and refining predictions as each new observation arrived. Amateur astronomers contributed by monitoring the sky for brightness variations and submitting photometric measurements, filling gaps left by limited telescope time or weather interruptions. This intricate network of observation underscored both the collaborative power and the fragility of modern planetary science. With every night, the orbital path became clearer, a hyperbolic inbound curve from interstellar space sweeping toward the inner solar system, carrying with it chemical and structural secrets from beyond the sun's influence. Patterns emerged slowly, subtle indicators of rotation and composition, each hinting at the alien origins of 3I Atlas. Yet the full story remained just out of reach. The global effort was a testament to the precision, patience, and anticipation required to track a celestial visitor that would not pause for human attention, whose arrival demanded absolute vigilance to capture fleeting glimpses of a universe operating on its own indifferent timetable. By early October, the parameters of the Mars observation window had been defined with razor-sharp precision. From October 1st through the 7th, the geometry of 3I Atlas's trajectory aligned perfectly with the Martian orbit, presenting the rare opportunity to capture fleeting data from a vantage point unmatched anywhere else in the inner solar system. This alignment was ephemeral. Days, hours, and even minutes became critical units of opportunity. Orbiters such as ESA's Mars Express and ExoMars Trace Gas Orbiter adjusted schedules, recalculating high-cadence observation sequences to maximize the return from every passing photon. NASA's MRO and MAVEN teams, though constrained by the ongoing federal shutdown, relied on pre-approved contingency plans, ensuring instruments could gather data without active communication with the public. Every instrument from high-resolution cameras to ultraviolet spectrographs was primed to observe the object's coma, detect subtle shifts in brightness, and trace any chemical emissions that might hint at its interstellar origin. Even a momentary misalignment or a cloud of Martian dust scattering incoming light could erase a year's worth of careful planning. In the quiet corridors of mission control, technicians ran simulations, cross-checked pointing sequences, and verified telemetry. The entire scientific infrastructure was oriented around a single objective: to seize what the universe was offering in this brief, unrepeatable moment. Citizen astronomers, meanwhile, maintained parallel observations from Earth, submitting real-time photometric data that could fill in temporal gaps or provide redundancy. Mars, usually a passive backdrop to robotic explorers, had become the solar system's most critical observatory, a transient stage where light from an interstellar traveler would speak volumes to those prepared to listen. In these 7 days, every second counted, and the margin for error shrank with each rotation of the planet, every orbit of a satellite, and every passing photon from 3I Atlas's fleeting presence. October 3rd marked the moment of closest approach, the day when 3I Atlas skimmed within 30 million kilometers of Mars, a distance that rendered even the most sophisticated cameras into rudimentary photon counters. At this range, the object's nucleus remained unresolved, a point of light that shifted imperceptibly against the background of stars. Yet every fluctuation in brightness, every subtle shift in hue, every expansion or contraction of the coma carried essential information. Scientists monitored the data streams with heightened intensity, aware that each second of observation could provide insight into the visitor's rotation, composition, and structural integrity. Instruments across multiple orbiters synchronized their exposures, attempting to capture overlapping photometric and spectroscopic readings to triangulate the object's physical properties. For a fleeting moment, the red planet's skies became a stage for interstellar revelation, its orbiters tracing the passage of matter formed in environments radically unlike our own. The hyperbolic velocity of 3I Atlas, coupled with its unpredictable spin and potential outgassing, made the task of data interpretation extraordinarily complex. Every photon collected had to be accounted for, every observation logged with meticulous precision, as these fleeting readings represented the only window into an object whose origin lay light-years away. The closest approach was both a culmination and a beginning. The culmination of months of preparation and anticipation, and the beginning of an intense analytical campaign that would seek to decode the subtle messages embedded in light and movement, translating a brief interstellar visitor's journey into human understanding. Observers could only watch, record, and hope that the universe, in its indifference, would offer a clear story within this narrow temporal corridor. Following the fleeting encounter with Mars, 3I Atlas pressed on toward perihelion, rounding the Sun at a distance of 1.36 astronomical units, or approximately 204 million kilometers. From Earth, the visitor disappeared into the Sun's blinding glare, leaving astronomers and orbital assets alike momentarily blind to its progress. Only spacecraft positioned far from the solar disk, such as ESA's JUICE at Jupiter, retained a chance to observe outgassing peaks and activity levels, while ground-based telescopes awaited the object's re-emergence months later. During perihelion, the object's thermal dynamics shifted dramatically. Increased solar irradiation could trigger sublimation of volatile compounds, alter coma structure, and even reveal fragments or unusual jet activity. This period was a silent drama, unfolding out of reach of most observers, where the laws of physics dictated processes beyond human intervention or control. Scientists could model the expected behavior, predict shifts in brightness, and anticipate chemical signatures, but direct verification had to wait. For mission planners, perihelion represented both a challenge and a tantalizing opportunity. Any anomalous behavior observed post-conjunction could indicate properties never before recorded in interstellar comets, potentially hinting at formation environments far different from anything in our solar neighborhood. The passage around the Sun was a reminder that interstellar visitors do not pause for human schedules. They operate on trajectories dictated by gravitation, momentum, and their own composition, indifferent to observation windows, bureaucratic calendars, or public curiosity. And yet, even in absence, 3I Atlas communicated through light curves, through modeled predictions, through the silent anticipation of the instruments poised to resume tracking as soon as the solar glare subsided. By late November, as 3I Atlas emerged from behind the Sun's blinding glare, telescopes across Earth scrambled to reacquire the interstellar visitor. The object, now distant and faint, required careful targeting. Its hyperbolic trajectory, refined by months of observation, left little room for error. Spectrographs scanned for residual gases and subtle traces of exotic chemistry, seeking lingering signatures of carbon compounds, water, ice, and other molecules that might reveal its birthplace. Light curves, carefully monitored, continued to record variations that hinted at rotation and surface heterogeneity. Every observation was compared against pre-perihelion predictions, a meticulous exercise in validation and verification, ensuring that nothing contradicted the established orbital path and physical expectations. Ground-based teams coordinated with orbiters still operational on Mars, ESA's distant missions, and a network of citizen astronomers who continued to monitor brightness and color. Each dataset, no matter how small, became a thread in the growing tapestry of interstellar knowledge. Despite the object's faintness, the campaign revealed the remarkable consistency of its hyperbolic trajectory, confirming that 3I Atlas adhered to the expectations set by early measurements, yet still held subtle surprises in its photometric behavior. In this post-conjunction period, scientists reconciled every observation with predictions, searching for anomalies, deviations, or chemical signatures that might indicate something extraordinary, a phenomenon beyond the ordinary parameters of cometary physics. The object's quiet reappearance reinforced both the challenge and the opportunity. Even as the solar system's instruments struggled against distance and dimness, the potential to glimpse matter from another star system remained tantalizingly real, a bridge between human curiosity and the silent vastness of interstellar space. Coordination between ESA and NASA became a central pillar of the observation campaign, a complex choreography of orbital assets and ground-based telescopes operating under tightly constrained schedules. European orbiters, including Mars Express and ExoMars Trace Gas Orbiter, executed high-cadence sequences designed to track the faint, rapidly moving interstellar visitor with maximum efficiency. Each pointing command was calculated to align with the object's predicted trajectory, allowing the HRSC and CAS imaging teams to capture photometric points and spectral data at critical moments. Simultaneously, NASA's MRO and MAVEN teams, restricted by the public shutdown, operated from pre-approved scripts, their instruments pivoting from routine atmospheric and surface studies to cometary observation. Commands were relayed through secure channels, ensuring continuity of data while adhering to legal and budgetary constraints. Communication between agencies involved careful timing, updated ephemerides, exposure sequences, and calibration routines were shared in near real time to ensure observations were complementary rather than redundant. The orchestration extended beyond orbital assets. Ground-based observatories in Europe, Asia, and the Americas synchronized their imaging and spectroscopic campaigns to coincide with moments when 3I Atlas would be most visible, maximizing coverage despite limitations imposed by weather, daylight, and the object's faint magnitude. Each photon collected was precious. Each spectral line analyzed could offer insight into the visitor's interstellar origin. In this network of interdependent operations, human precision and coordination became as critical as the physics being observed. The campaign represented not only a technical and scientific achievement, but also a philosophical affirmation of global collaboration, uniting diverse institutions, nations, and observers in the shared pursuit of understanding a messenger from beyond our solar system. Within NASA, the Red Watch crew became the invisible heartbeat of the interstellar observation campaign. These skeleton staffers, designated as essential personnel under the Anti-Deficiency Act, maintained critical spacecraft operations while the broader agency lay dormant in compliance with the government shutdown. Their presence was silent yet indispensable. No press releases or public briefings bore their names, but every orbital adjustment, every telemetry check, and every command execution passed through their hands. Working in shifts, the crew meticulously verified instrument health, cross-checked pointing sequences, and logged each action with bureaucratic precision, ensuring that the data pipeline remained uninterrupted despite the blackout. The legal constraints imposed a unique challenge. While they could operate spacecraft and gather data, they were prohibited from releasing any information beyond operational necessities. Every observation, every exposure sequence, every minor anomaly had to be documented internally without public acknowledgement. The team balanced technical rigor with operational secrecy, navigating both the delicate instruments aboard Mars Reconnaissance Orbiter, MAVEN, and other assets, and the strictures of law that forbade any communication outside mission-critical channels. Their work ensured that even in the absence of public oversight, the interstellar visitors' transit past Mars would be captured with integrity. In quiet control rooms, lit only by the glow of instrument monitors and the soft hum of servers, these unseen operators became the custodians of an interstellar encounter, guardians of photons and trajectories, ensuring that the fleeting passage of 3I Atlas would not be lost to bureaucracy or the indifferent passage of time. Their labor, though invisible to the outside world, underpinned every subsequent analysis, comparison, and reflection that would define humanity's engagement with this rare visitor from beyond. The global network of observers extended far beyond NASA and ESA, encompassing mission teams from China, the United Arab Emirates, and a dedicated community of citizen astronomers. China's Tianwen-1 team at BACC monitored 3I Atlas with precision instruments, capturing photometric and astrometric data, while the UAE's HOPE mission contributed complementary measurements of brightness, fluctuations, and coma activity from orbit. Each high-resolution camera, spectrograph, and ultraviolet sensor added layers of insight, building a composite portrait of the visitor from interstellar space. Citizen astronomers, operating backyard telescopes and automated tracking software, submitted real-time observations to the Minor Planet Center, filling observational gaps caused by weather, limited telescope time, or orbital constraints. Their data, though less precise than institutional measurements, played a critical role in reinforcing trajectories, confirming brightness variations, and highlighting anomalies that might otherwise have gone unnoticed. Across continents and time zones, human attention synchronized with the passage of photons traveling for light years, uniting professionals and amateurs in a shared pursuit of understanding. Every observation, no matter the scale, contributed to a delicate tapestry of information, ensuring redundancy, cross-verification, and continuity of data collection. The collaboration underscored a profound truth. No single agency, telescope, or observer owns the sky. Each participant, from seasoned orbital operators to dedicated volunteers, became part of a distributed intelligence, a collective witness to a rare interstellar visitor. In this orchestrated vigilance, the margins of error narrowed, and humanity's capacity to observe, interpret, and learn from a cosmic stranger reached its zenith, creating a fleeting moment when cooperation, technology, and curiosity converged perfectly under the indifferent vastness of space. The legal framework of the Anti-Deficiency Act imposed a profound silence on NASA's public communications, creating a blackout that coincided almost theatrically with 3 Atlas's transit past Mars. Federal law dictated that agencies could not obligate funds beyond congressional approval, effectively suspending outreach, press briefings, and public updates, while operational tasks essential to life or property could continue under strict oversight. The result was an invisible firewall. Spacecraft remained fully functional, commands were executed, and telemetry flowed uninterrupted. But the narrative, the human story of this interstellar encounter, was suspended. Websites displayed stark notices of closure, social media channels went dark, and automated news feeds offered no commentary on the rare visitor streaming through the solar system. The paradox was striking. The instruments of discovery operated at peak capacity, capturing photons from a body formed in a distant star system, yet the public had no access to these moments in real time. Every furlough notice, every locked account, and every silent blog became part of a broader temporal tension, emphasizing the dichotomy between operational continuity and informational absence. Within this framework, mission operators were acutely aware that their work, while unseen, was essential. The blackout did not diminish the scientific rigor. Rather, it enforced discipline, confidentiality, and focus, isolating raw observation from public speculation until a future release. In this enforced silence, the passage of 3I Atlas became a study not only in interstellar physics, but also in the interplay of law, bureaucracy, and human perception, revealing how cosmic events intersect with human structures in ways both subtle and profound. The act of observing continued, but the act of telling the story waited, amplifying the tension between knowledge and awareness, between photons collected and narratives constructed. In the absence of public updates, Mars orbiters reduced their instruments to their most fundamental tasks: photon counting. High-resolution cameras became precision counters of incoming light, registering subtle variations in brightness as 3I Atlas moved across the Martian sky. Spectrometers monitored color shifts in the coma, hinting at ice content, dust distribution, and potential chemical anomalies. Ultraviolet sensors recorded emissions from transient gases, seeking traces of volatile molecules that might reveal exotic composition or unexpected activity. Every exposure was timed to the second, each sequence carefully pre-approved to maximize coverage during the week-long window. Scientists calculated integration times, ensured proper calibration, and adjusted for the planet's rotation, orbital velocity, and atmospheric interference. The nucleus itself remained unresolved, smaller than a pixel even on the most powerful instruments, yet the coma, the faint halo of material surrounding the object, offered a wealth of information. Rotational modulation in the light curve hinted at asymmetries in shape or composition, while brightness fluctuations tracked the dynamics of outgassing or sublimation. Even minor deviations in the photon count could signal significant physical properties, from spin rate to mass distribution. For 7 days, every photon mattered. Each represented a rare glimpse into an object originating from a star system beyond our own. The process was painstaking, methodical, and silent, with engineers and scientists acting as custodians of information, ensuring that when the blackout lifted, the data would form a coherent, analyzable record of a fleeting interstellar passage that might never be repeated. Citizen scientists played an indispensable role in the campaign, bridging observational gaps that institutional resources could not fully cover. Individuals like Priya Ralo, working from modest backyard telescopes, meticulously tracked variations in brightness, submitted photometric data, and compared observations against official predictions. Though their instruments lacked the precision of orbital assets, these contributions filled temporal and spatial gaps, offering continuity when professional observations were constrained by weather, orbital limitations, or bandwidth. Networks of amateur astronomers coordinated through online platforms, sharing real-time measurements, plotting light curves, and discussing anomalies that might otherwise have gone unnoticed. Each observation, however small, reinforced the global effort, creating a distributed monitoring system that augmented the official campaigns from NASA, ESA, China, and the UAE. The contributions of these volunteers underscored a profound principle. The sky belongs to no single agency or nation. Every photon, every data point, became part of a collective narrative, ensuring that the fleeting passage of 3I Atlas was captured from multiple vantage points. Citizen observations also acted as a safeguard against error, cross-checking professional data and offering redundancy in case of instrument failure. In essence, these amateurs became part of an invisible yet critical observational fabric, extending humanity's reach and perception across millions of kilometers of space. Their meticulous recordings allowed the object's hyperbolic trajectory, rotational characteristics, and coma behavior to be documented with unprecedented completeness, demonstrating the extraordinary synergy between professional rigor and passionate curiosity. The collaboration between dedicated volunteers and established institutions exemplified how humanity could collectively witness a visitor from beyond the solar system, transforming isolated photons into a shared understanding of the cosmos. The absence of public communication created fertile ground for speculation, as social media and online forums buzzed with conjecture. In the vacuum left by the blackout, rumors multiplied, ranging from mundane interpretations to extraordinary claims. Screenshots of the last ESA blog posts circulated alongside amateur light curve analyses, giving rise to threads debating the object's nature, origin, and trajectory. Some suggested a spectrum anomaly, a hint of chemical composition that might defy known cometary behavior. Others posited more fantastical ideas, from secret spacecraft monitoring to classified research beyond public disclosure. The interplay of uncertainty and imagination amplified the sense of mystery, transforming a scientific campaign into a cultural event shaped as much by human perception as by photons from the object itself. Observers speculated on coincidences, questioning whether the timing of the government shutdown and the Mars window was purely bureaucratic or hinted at deliberate concealment. Each gap in updates, each unexplained delay in data release became a seed for narratives, blurring the line between fact and inference. Yet behind this noise, the scientific record remained methodical and precise. Every photon, every pointing sequence, and every spectral measurement was logged in mission archives, immune to rumor. The tension between documented observation and public speculation highlighted a fundamental truth about science. Data can exist independently of narrative, waiting for rigorous analysis before stories can be confirmed or refuted. In this environment, the interstellar visitor became more than a comet. It was a mirror, reflecting human curiosity, imagination, and the social dynamics that arise when knowledge is both tantalizingly present and frustratingly inaccessible. As the blackout persisted, scientists and analysts considered 6 competing explanations to reconcile the timing, observations, and unusual circumstances surrounding 3I Atlas's Mars window. The first, the most prosaic, invoked bureaucratic coincidence, a routine government shutdown dictated by fiscal calendars, intersected with a rare but natural celestial event. Second, environmental factors, such as solar wind variations or Martian atmospheric interference, could produce transient observational anomalies, mimicking gaps or inconsistencies in data. Third, speculation turned to the object itself. Perhaps an unusually massive or metal-rich nucleus would manifest in unexpected spectral features or trajectory perturbations. The fourth possibility considered classified operations, the idea that certain high-priority missions might operate in parallel, with data inaccessible to the public but fully documented internally. Fifth, a hypothetical third-party intercept technology, unknown to any official agency, suggested intervention or observation beyond sanctioned capabilities, an idea with no precedent yet intriguing in a universe that often surprises. Finally, the most extraordinary and provocative explanation entertained the possibility of an engineered artifact, a body not born naturally but constructed and disguised as a comet or icy object, traversing interstellar space with purposeful intent. Each hypothesis demanded rigorous verification. Orbital dynamics had to match independent observations, spectral lines needed confirmation, and any deviations had to withstand scrutiny across multiple instruments and agencies. The discussion exemplified the interplay between empirical evidence and imagination, illustrating how scientists systematically explore even the most improbable scenarios while adhering to strict standards of proof. In this crucible of inquiry, the balance between possibility and plausibility became central, reminding observers that while human speculation is inevitable, only reproducible, verifiable measurements would ultimately determine the truth of the interstellar visitor's passage. To navigate the uncertainty surrounding 3I Atlas, scientists relied on a meticulous receipts checklist, a rigorous protocol ensuring every observation could be verified and audited once the blackout ended. This checklist encompassed multiple layers. Minor planet center updates provided hyperbolic elements, eccentricity measurements, and velocity data, while ESA's Mars Express and ExoMars TGO contributed raw images, spectral information, and precise pointing logs. NASA's post-shutdown archives preserved every command, telemetry packet, and exposure sequence, documenting operational continuity despite public silence. Cross-referencing light curves, spectroscopic data, and orbital positions from ground-based telescopes and space-based observatories ensured consistency and minimized the risk of anomalies arising from instrumentation error. Every photon collected, every subtle variation in brightness, and every spectral line was catalogued for later analysis, creating a comprehensive record of the object's passage. This system of verification was not intended for immediate publication. It existed to separate signal from noise, rumor from record, ensuring that once the blackout lifted, scientists could reconstruct the encounter with confidence. The receipts checklist exemplified the precision and rigor required to transform transient cosmic phenomena into verifiable knowledge. Even amidst speculation, uncertainties, and the human imagination's natural tendency to fill gaps, the archive ensured that the eventual narrative of 3I Atlas's journey would rest on empirical evidence rather than conjecture. Through this painstaking process, humanity's encounter with an interstellar visitor was preserved with integrity, bridging the ephemeral passage of photons with the enduring permanence of recorded science. Through careful observation and rigorous data collection, the hyperbolic path of 3I Atlas was confirmed, solidifying its status as a bona fide interstellar visitor. Measurements indicated velocities and eccentricities far exceeding the parameters of typical solar system comets, affirming that the object was unbound and inbound from beyond the Sun's gravitational influence. Cross-checked observations from multiple agencies, spanning ESA, NASA, Chinese, and UAE missions, demonstrated remarkable consistency. The object adhered to the predictions derived from early detection in July, leaving little room for alternative interpretations. Even subtle deviations in rotational light curves, coma asymmetries, and minor spectral variations were accounted for, confirming that 3I Atlas's behavior remained within the expected range for a hyperbolic interstellar object. Its passage offered unprecedented opportunity to study matter formed under extraterrestrial conditions, providing a rare glimpse into the chemical and physical properties of a body originating in a distant star system. The confirmation of trajectory not only satisfied scientific curiosity, but also underscored the global coordination required to track such fleeting phenomena. Each data point, meticulously logged and later cross-referenced, contributed to a cohesive narrative of the object's journey, bridging months of observation and thousands of kilometers of orbital monitoring. In affirming the hyperbolic path, scientists validated both the predictive models of interstellar dynamics and the precision of a distributed observational network. 3I Atlas had traversed space, indifferent to human schedules, yet through collective diligence, its transit became a documented event, a testament to the intersection of natural laws, human foresight, and the enduring drive to understand the universe's rarest visitors. Spectroscopic analysis of 3I Atlas provided critical insight into its composition, revealing subtle traces of ice, dust, and possible exotic molecules that hinted at a formation environment starkly different from anything found in the solar system. Ultraviolet and infrared observations detected faint emissions consistent with volatile compounds, including water, ice, carbon monoxide, and traces of hydrocarbons, though the precise abundance of each remained challenging to quantify due to the object's distance and faintness. Variations in color across the coma suggested heterogeneity, pointing to a surface composed of mixed materials rather than a uniform icy nucleus. The object's reflective properties indicated a relatively low albedo, consistent with a dark, carbon-rich outer layer, while intermittent brightening suggested sporadic outgassing or rotation exposing fresher, more reflective material. Combined, these data provided a chemical fingerprint, offering a rare window into the physical processes shaping interstellar bodies and hinting at the violent, frigid conditions of its birth. Comparisons with known comets from within our solar system revealed both similarities and striking differences. While familiar processes such as sublimation of volatiles occurred, the speed, trajectory, and subtle spectral anomalies suggested origins beyond our planetary neighborhood. Each photon collected in these spectra became a messenger from a distant star system, encoding information about temperature gradients, material composition, and chemical evolution that had unfolded over millions of years. In synthesizing these observations, scientists were not merely cataloging a transient visitor, they were reconstructing a fragment of another stellar environment, using light and motion to bridge the interstellar gulf and illuminate a realm previously beyond reach. Comparative analysis placed 3I Atlas alongside its interstellar predecessors, Oumuamua in 2017 and Borisoft in 2019, revealing both echoes of similarity and unique divergences that challenged existing cometary models. Like Oumuamua, 3I Atlas displayed a hyperbolic trajectory, traveling at velocities incompatible with solar system binding. Yet, unlike Oumuamua, it exhibited a discernible coma and photometric variability, suggesting active outgassing. Borisoft, while more conventional in its chemical composition, still defied expectations with a velocity and trajectory that stressed prior assumptions about interstellar object frequency and dynamics. By placing 3I Atlas within this sparse lineage, scientists gained comparative data, testing hypotheses about interstellar formation, compositional diversity, and the physical forces shaping such objects during long-term journeys across the galaxy. Patterns emerged. High eccentricities, non-repeating arrival intervals, and unique rotational properties underscored the challenge of predicting interstellar comet behavior. Yet 3I Atlas also presented anomalies absent in previous encounters: subtle spectral features, rotational modulation in brightness, and potentially exotic molecular signatures suggesting variations in composition and history that could reflect differences in the stellar environments from which these objects originated. Each new piece of data prompted recalibration of theoretical models, refinement of orbital predictions, and reconsideration of the mechanisms by which interstellar matter traverses the void between stars. Through this comparative lens, 3I Atlas was not only a singular phenomenon, but a key reference point in understanding a broader, rare class of celestial visitors, offering an unprecedented opportunity to probe the chemical, physical, and dynamical diversity of bodies formed far beyond the Sun's influence. Despite the sophistication of modern instruments, the observational campaign confronted inherent limitations. Even the most powerful cameras aboard Mars orbiters and distant telescopes could not resolve the nucleus of 3I Atlas. At tens of millions of kilometers, the object's core remained a subpixel point of light, unyielding to direct imaging. Spectrometers and ultraviolet instruments, while capable of detecting the faintest emissions, were constrained by signal-to-noise ratios, requiring long integrations and careful calibration. Observers relied on indirect measurements, variations in coma shape, fluctuations in brightness, and spectral line strengths, each offering glimpses into the object's size, rotation, and chemical composition. The subtle interplay between light curve modulation and rotational dynamics provided clues to shape and surface heterogeneity, while photometric color shifts suggested localized differences in material composition or sublimation activity. These constraints demanded rigorous attention to detail, cross-validation between instruments, and meticulous error analysis to ensure reliability. Every exposure was designed to maximize information while minimizing uncertainty, acknowledging that even minor deviations could dramatically affect interpretations. In this context, limitations were not merely technical obstacles, they were intrinsic features of observing a transient interstellar object at immense distances. Scientists accepted that some mysteries, nucleus shape, internal structure, exact mass distribution might remain unresolved, yet the collective dataset from multiple observatories still permitted inferences about physical and chemical characteristics. The constraints emphasized both the fragility and precision of human observation, revealing the extraordinary lengths required to extract meaningful knowledge from a visitor born in a star system light years away. Amidst these observational constraints, scientists began to discern subtle patterns in 3I atlas behavior that hinted at underlying physical processes. Light curves revealed periodic fluctuations, suggesting rotational dynamics, while asymmetries in the coma indicated heterogeneous outgassing or irregular surface features. Observers noted minor color variations, implying compositional diversity across the object's exterior, and occasional bursts of brightness hinted at transient jets of gas and dust, possibly driven by localized sublimation of volatile compounds. These patterns, faint and often bordering on the noise threshold, were cross-checked across multiple instruments and observatories to verify consistency. Data from Mars orbiters complemented ground-based photometry, creating a composite record that allowed scientists to model rotation rates, approximate shape, and even potential mass distribution. Spectroscopic observations, though limited, suggested correlations between light curve anomalies and specific molecular emissions, offering clues to the physical interactions between the nucleus and solar radiation. Each new insight emerged cautiously, filtered through rigorous error analysis to distinguish real phenomena from instrumental artifacts or environmental effects. In interpreting these subtle signals, scientists recognized the importance of coherence across independent measurements. A pattern observed by ESA, NASA, and amateur astronomers carried far more weight than an isolated anomaly. The discovery of these patterns transformed what initially seemed like a faint point of light into a dynamic, evolving body, revealing glimpses of the physical mechanisms governing an interstellar traveler. Even in its silence, 3I Atlas communicated the story of its structure and activity, inviting careful reconstruction by those attuned to the delicate language of photons and motion. With the observational data in hand, scientists rigorously tested existing theoretical models against the measured properties of 3I Atlas. Standard cometry dynamics, derived from centuries of observing solar system bodies, were compared to the hyperbolic trajectory, rotational characteristics, and photometric variations recorded during the Mars window. Models accounting for sublimation, outgassing, and coma development were evaluated to see if they could replicate observed brightness fluctuations and color shifts. Deviations prompted refinements in assumptions about composition, mass distribution, and rotational inertia. Interstellar formation theories were also invoked. If 3I Atlas originated in a distant, colder, or more turbulent stellar environment, its physical and chemical properties might differ from familiar solar system comets, influencing behavior as it approached perihelion. Computational simulations modeled the object's spin, thermal response, and sublimation under varying assumptions, comparing predicted light curves and spectral signatures with actual measurements. Every discrepancy prompted further investigation. Each alignment reinforced confidence in the models. This iterative process allowed scientists not only to describe the behavior of a single interstellar object, but to expand understanding of the broader class of hyperbolic visitors. Observations that challenged assumptions about volatile content, rotation, or coma asymmetry catalyzed revisions in predictive frameworks, refining the methods used to anticipate behavior of future interstellar intruders. Through systematic comparison between observation and theory, 3I Atlas became both subject and teacher, a bridge between empirical measurement and conceptual understanding, illuminating the strengths and limitations of human models when confronted with the uncharted physics of interstellar matter. The passage of 3I Atlas presented potential challenges to established paradigms, forcing scientists to reconsider assumptions about the frequency, composition, and dynamics of interstellar objects. Its hyperbolic trajectory, and high velocity confirmed that bodies from beyond our solar system could traverse the inner planetary region without significant perturbation, highlighting a population of visitors that had been, until recently, effectively invisible. Subtle anomalies in light curves, coma, asymmetry, and spectral lines raised questions about the diversity of material in other stellar systems and the processes that shape it. Were certain molecular compounds, observed faintly in the coma, evidence of chemical pathways not seen in the solar system? Could variations in rotational behavior hint at internal structure or collisional history unique to interstellar environments? These inquiries touched on fundamental astrophysical principles, the transport of material across light years, the survival of icy bodies in interstellar space, and the limits of predictive modeling based on a single solar system's experience. In grappling with these questions, scientists recognized that each new interstellar encounter could reshape their understanding, informing not just cometary science but planetary formation theories, the distribution of volatiles in the galaxy, and even the potential for prebiotic chemistry in distant systems. The passage of 3I Atlas became more than an observational milestone. It was a philosophical and scientific challenge, reminding humanity that the universe contains processes and structures that may defy established frameworks, and that each rare visitor offers a crucial test of our theories, assumptions, and readiness to expand knowledge in the face of the unknown. As 3I Atlas receded beyond the immediate observational corridor of Mars and Earth, scientists began to reflect on the philosophical implications of its passage. Here was a fragment of another stellar system, traveling across light years to briefly intersect with humanity's instruments, indifferent to human presence, law, or attention. Its silence, its precise adherence to physical laws, and its transient appearance reminded observers of the universe's vast scale and the fragility of human perception. In contemplating 3I Atlas, researchers and enthusiasts alike confronted questions of perspective, temporality, and significance. What does it mean to witness an event whose causal history stretches across millennia, yet whose observable duration is measured in days? The visitor became a lens through which to explore human understanding itself, highlighting the limits of observation, the necessity of patience, and the provisional nature of knowledge. It prompted reflection on the interconnectedness of global scientific effort, the intricate choreography of observation and prediction, and the humility required to acknowledge both the power and the limitations of human inquiry. In its quiet passage, 3I Atlas offered a cosmic meditation, a reminder that the universe is vast, indifferent, and filled with phenomena that will test our models, challenge our assumptions, and inspire a profound sense of wonder. Its transient journey underscored the beauty of fleeting opportunities, the responsibility of careful observation, and the enduring capacity for curiosity to bridge the gulf between the known and the unknowable. The blackout episode surrounding 3I Atlas illuminated the delicate balance between operational necessity and public trust in science. While NASA and allied agencies continued their observations in strict compliance with the law, the absence of real-time updates left the global community in suspense. Public curiosity surged, fueled by speculation, partial information, and the intrinsic fascination with rare cosmic events. Scientists and communicators recognized the tension. Essential spacecraft operations could not pause, yet the inability to share findings risked eroding confidence in transparency and accountability. Social media threads, amateur analyses, and speculative reports became surrogate narratives, filling the vacuum with both insight and misinformation. The episode highlighted the importance of structured, verifiable records, such as the receipts checklist, to ensure that when the blackout ended, the truth would emerge unambiguously. In this interplay between science and observation, humanity confronted a deeper question. How does society interpret phenomena that unfold beyond immediate perception when data are collected but narratives are delayed? The situation underscored the responsibility of scientific institutions to safeguard both the integrity of research and the public's trust, demonstrating that transparency is not merely a procedural concern, but a philosophical commitment. In observing the cosmos, humans must navigate not only the technical challenges of measurement, but also the social dynamics of perception, interpretation, and expectation. The interplay of law, communication, and observation during the 3-eye Atlas window thus became a microcosm of the broader challenge inherent in humanity's engagement with the universe, balancing precision, secrecy, and trust in the pursuit of knowledge. As the Mars window closed and 3-eye Atlas receded from immediate view, the global scientific community turned to verification and reconciliation of the collected data. Every photon, every light curve, and every spectral line underwent rigorous cross-comparison among ESA, NASA, and ground-based observatories. Observers reconciled measurements against predictive models, ensuring consistency across multiple instruments, platforms, and geographic locations. Analysts scrutinized potential anomalies, subtle deviations in rotational light curves, minor spectral features, and any unexpected coma behavior, testing them against known physical laws and interstellar formation scenarios. This meticulous process distinguished genuine phenomena from instrumental noise or observational artifacts, transforming raw data into coherent, verifiable knowledge. The post-shutdown audit allowed scientists to confirm which observations survived scrutiny, reinforcing or challenging pre-existing models of interstellar comet behavior. Patterns identified during the observation window, rotational dynamics, compositional heterogeneity, and hyperbolic motion were contextualized within the framework of previous interstellar objects like Oumuamua and Borisoft, offering comparative insight while highlighting unique characteristics of 3-eye Atlas. The reconciliation phase demonstrated the robustness of international coordination, the reliability of multi-instrument verification, and the necessity of patience in translating fleeting observations into enduring understanding. In this way, the campaign transformed ephemeral cosmic light into a detailed narrative of motion, composition, and interstellar provenance, ensuring that the encounter with 3-eye Atlas would stand as a benchmark for both science and the philosophy of observation. In the final hours of the Mars observation window, 3-eye Atlas completed its passage, slipping quietly beyond the reach of orbiters and ground-based telescopes alike. Its hyperbolic journey, traced in thousands of data points and hundreds of hours of observation, left behind a complex mosaic of photometry, spectroscopy, and astrometry, a testament to both the object's interstellar origin and the human effort marshaled to study it. Scientists reflected on the transient alignment that had transformed Mars into a cosmic observatory and revealed the meticulous coordination required to capture such fleeting phenomena. While the visitor had passed, the questions it raised lingered. The composition and structure of its nucleus, the processes governing interstellar bodies, and the broader implications for planetary formation and chemistry across the galaxy. Observers acknowledged the extraordinary confluence of chance and preparation, where bureaucratic timing, orbital mechanics, and international collaboration intersected to make a single week of observation possible. The object's passage underscored the ephemeral nature of opportunity in astronomy, moments that may not recur for decades or centuries, demanding precision, vigilance, and patience. In its quiet retreat, 3-eye Atlas left humanity with both knowledge and humility. a reminder that the universe operates on scales and rhythms indifferent to human attention, yet that careful observation can transform transient phenomena into enduring understanding. Its fleeting presence became an emblem of cosmic perspective, highlighting the beauty, complexity, and fragility of the moments when human curiosity meets the infinite vastness of space. As the glow of 3I Atlas faded into the interstellar darkness, the universe seemed to exhale a quiet sigh, leaving Mars and the earthly observers to contemplate what had just passed. Days of meticulous observation, countless photons counted, and spectra analyzed now settled into a serene archive, a record of a fleeting visitor that bridged the gap between star systems and human curiosity. The instruments, once focused intensely on a point of light moving across millions of kilometers of space, relaxed back into routine, their sensors returning to the rhythms of atmospheric studies, orbital tracking, and planetary science. Yet the echo of that week lingered, a reminder of the impermanence of opportunity and the magnitude of what is possible when preparation meets chance. Humanity had glimpsed matter formed in alien stellar environments, studied the dance of ice, dust, and energy across the void, and confirmed that the cosmos continually offers lessons in both humility and wonder. The Red Watch crews, ESA teams, citizen astronomers, and every unseen operator became threads in a tapestry that preserved the memory of an interstellar traveler, their labor invisible but enduring. And in the quiet aftermath, reflection spread. The universe is indifferent, vast, and filled with phenomena that arrive unannounced, yet through observation, patience, and collective effort, even the most transient visitor can teach us about the nature of matter, motion, and time. As the photons scattered by 3I Atlas finally merged with the dark, the moment softened into thought, a cosmic whisper reminding all who had watched that understanding often comes not with spectacle, but in measured attention, careful observation, and the patience to record, analyze, and wonder. The object was gone, but the reflection it inspired remained, suspended in the minds of those who had looked skyward and seen the universe in motion. Sweet dreams,